Welcome back to the series on epsilon delta. So our next step is going to be the absolute value. So on the right hand side you can see that the absolute value function is definitely different. So it does pose a little bit of a problem because of the absolutes. So sometimes students don't know how to deal with that when they're doing epsilon deltas. So I thought to do this video just to show you a couple of examples and then generalize for any absolute value. So you can transform it any way that you like. So you can translate it, you can compress it, stretch it, etc. And you will see that actually finding the delta for a given epsilon is not that difficult, and it pretty much follows exactly what you would do in the linear case. So I have done the entire series in terms of doing the definition itself. So this particular definition of the epsilon delta limit, explaining it. You know, I've done examples on linear cases, on quadratic cases, on cubic cases, and now I'm doing the absolute ones. So I'm going to put up, a link, and that particular link is going to be to the playlist itself. So you can hit on that playlist and you can walk yourself through numerous examples. My goal in this video is going to be just to concentrate on the absolute value and to show you, what kind of things, what tricks you can use to find your deltas. All right. And my goal is going to be indeed just to find the delta. We are going to be concentrating on the steps. If someone gives us an epsilon, we want to find a delta in terms of the epsilon. And then, showing this final step, once you have a delta, you can substitute it back in to just make sure that it is indeed does hold. And you would see that in the previous videos that I've done. So maybe I'll just do one, okay, which is complete, and then the rest I'll just find the delta for. So let's dive into this first example right here. So it's a simple limit. So x is approaching -2 of the absolute value of x, and we know that it's equal to 2. So how are we going to structure this? So again, so step one is we have to actually state what we're doing. So there it is. I'm just copying and pasting it so I don't have to write it down and just make the video long. Okay, so that's the first thing that we'll do, and then we're going to try to make this connection between your function and the limit, and then x minus a. So it's going to be some small domain that we need. Okay, so within here. So let's give it a go. All right, so now how are we going to be making this connection? So here is our f of x, which is going to be x minus our limit, which is 2, right there. And our ultimate goal always is, somehow to connect it in this way. So you've seen this in the previous videos that I have done. So our ultimate goal is going to be x, and this is minus -2, which is your a. So we are actually looking for this c. We want to be able to bound this in some way if necessary. And then we want to have a factor like this. So notice that this factor is going to be x plus 2. All right, that's what we want to do. So how are we going to do that? Well, we have a negative in there. So we're going to have to try to make a few assumptions and statements to make this hold. So first of all, notice that our x is approaching -2, right? And because it is approaching -2, we can make an assumption that we're going to live within x, which is on the negative side, all right, of the axis. So we don't necessarily need to go on the positive side. So I can say, for instance, all right, well, let's assume. So assume, okay, so we're going to take that we're going to be bounding, so around, so this is x minus the -1. Let's assume that this is, going to be within 1. So again, what does that mean? So within here, so this is going to be right here, because we're approaching -2. So we have, this is -1, and this is going to be -3. All right, so let's assume that it's going to be within there. So if it is in there, so that means that in this entire domain right here, this value is negative, meaning the value for x is negative. So if the value for x is negative, then what do we know about this right there? So let's duplicate this. Well, what we know is that the absolute value of this is the same thing as -x, right? Because if x is going to be negative, then that putting that negative in front is actually the definition of the absolute. So that means the negative and negative cancels and makes it positive, which is exactly the absolute value. Now, why am I doing that? Because notice that right here, if I do this, then it actually falls out. I can now take out the negative, and I'm going to get x plus 2 right there, which is exactly what I wanted. This negative is gone because of the absolute value, so what you have left is x plus 2, which is exactly what we wanted here. Now, RC is 1, okay, so we don't write it. Of course, in math, we don't need to write it, okay, but we have that 1 right there. So in order to finish and get our delta, so now that our delta is going to be, so right here, so this is supposed to be less than epsilon, so that entire thing, and this just simply means that x plus 2 is going to be less than epsilon divided by 1, or just epsilon, which means that our delta is going to be, and you can certainly pick the minimum between 1 and just simply epsilon. Now, this is actually an overkill, but because of the fact that I want it to be to the negative, I could have chosen this to be really anything, right, on the negative side. So it didn't have to be 1. If I chose it to be 2 right there, that would have worked as well. So notice that it would still keep me, so right here, this would have been 0, okay, if I have chosen this to be 2, and this would have been negative 4. So it still would have been all in the negative side. So that's all that I wanted, because I wanted this to hold, right? I wanted to write this out so that I can now transform it and then get x plus 2. Now, again, that's a little trick. That's something that you kind of have to think about when you're taking the limits. And okay, where is it? What boundary am I working around with? Because if you don't and you leave it just as the absolute value, you're going to run into a problem, and you won't be able to get this factor out, which is what you need. So that's what I have done. So now within here, the next step, so step number 2, is this one. And so there, if we know our delta, so here it is, so here's our delta right there, and this is what we want to be able to show. So, you know, does this actually hold, okay, within here? Well, so you can start off and take this whole thing in. So we're basically now just repeating the process. So this is going to be, all right, so this is negative x, okay, so that's right there on the assumption that we are, okay, within, so this is our delta, so between 1 and epsilon right there. So we know that this is the case, and therefore this is going to be negative 2, which is just equal to, you take out the negative, so you're going to get x plus 2, which is going to be, so this right here, okay, is going to be just your epsilon, right? So this is what we have. It's supposed to be less than epsilon right there. All right, so that's this. And that's what we wanted to be able to show. So this is always kind of an overkill, I thought, but I do understand it. You know, I've done now numerous proofs. You know, you do have to kind of make it formal and actually show, you know, so the step above, you've just found your delta, and now you actually have to see that if you are indeed within here, so within that particular domain, then this holds true. So that's why I had to put this out, okay, and kind of go in reverse and then do the whole thing again, okay, to show somebody that indeed it is true. Okay, so now for this example, if we now take out the decimals, so here's decimals, so let me zoom in, so we're around negative 2, so you can see there, all right, so I have that set up, so my C is equal to 1, okay, so that gives me my delta is the minimum between 1 and epsilon over 1, okay, which is just simply epsilon in this case, so they'll be the same. And you will notice, so between the blue, well, I've set epsilon here to 0.12, and that's delta as well. So whenever you are within that boundary, okay, so within delta away, notice that your limits, okay, that you have it, okay, so within the red boundaries, you're going to be sticking. So meaning your function is indeed within those limits. And actually this one is identical. So epsilon and delta are equal to each other. All right, so it nicely shows that, and then you can make this bigger. Okay, and this actually updates. I'll put the code for this as well so that you have it. I'll put it in the description below so that you can play around with this, and you can generalize it. You'll see it in the other example. So you can make this, bigger and bigger, right? So it just adjusts, okay, and it actually is displaying the values for us as well. And you can make it really tiny, so because that's, in the limit we would have been going tiny. So let me zoom in here so just that you can see, okay, that it still is holding. All right, so that's great. So we have found now our delta for this example. So here's our second example. So this one is a little bit more challenging. It's more involved. So notice that it's absolute values. So we're actually transforming this one. Okay, so the absolute value, so the parent function. So let's see how we're going to find our delta here. And I'm only going to find our delta, and then we're going to display it back on decimals just to see what's happening. All right, so let's write it out. All right, so this is what we have. So here's our f of x minus our L. So we just simplified it right here. Notice what we have. We have a 3 and a 3, so I can take that out. So that's going to leave me now with x plus 2 minus 1. Okay, so that's what I would have right there. And now I'm going to be working around -1. So, again, I'm on the negative side, so you can certainly play that game again. But instead, I'm going to actually use an inequality. Okay, so what happens is, so let me kind of rewrite this. I'm going to write this. I don't think that this is a far stretch for you. Okay, so I can see that I have a minus. Now I can put this 1 inside of the absolute values, like this. And it's still equal to each other. Obviously, it's an overkill. I don't need that absolute value. But why I'm putting this in here is because of this. Because we know, or I don't know if you know, but here is an inequality, which is standard inequality. If A and B are real numbers, doesn't matter what they are, positive, negative, 0, this inequality is always less than or equal to A minus B. All right, so this always holds. Now you can convince yourself of this. Now at some point I'll probably do a proof of this as well. Okay, if I do, you'll see the link, okay, up above right there. So eventually if I link this up, I haven't proved it yet. So if you know this, then I can use this trick right here. Now what I mean, so this is like your A, right, and this is like your B right there. So what we would have is I can rewrite this. Instead of having it in absolute values right here, I can drop the absolute values right there. So that's what I'm going to do. Now I have to be careful because now it is less than or equal to, and that's fine. That doesn't cause us any issues. We want something which is bigger than the function minus the limit. So this is going to be 3, and we're going to get, this is x plus 2 minus the 1. All right, and this is what we have right there. Now, once you do this, so notice what happens, then this right here is going to be, now this is just x plus 1. All right, so that's what you're going to get right there. Now, because of the x plus 1, well, this is exactly what we wanted. So notice within here, because we are approaching -1, so we want to relate this function back in to, indeed, to x. We want to have a connection with this, right? But this is nothing else just by x plus 1, okay, which is exactly what we see right there. So now we just want this to be less than epsilon, and therefore we can divide by 3, and that will tell us that the delta is going to be, in here, is equal to simply epsilon over 3. So we don't necessarily need any tricks or anything like that. This will hold true. All right, so we need epsilon over 3. Now, what I would want you to notice is that if you go back to the original, that 3 was the number which was in front right here. It had nothing to do with this and nothing to do with that, right? It just had this. And if you recall, and you'll see this, okay, with the linear case, with the slope, right? If this wasn't here, if the absolute values weren't here, this would have been just 3x plus 3 minus 1, and we would have been able to write it out as a regular linear function, so just a line. And we know that indeed we would be dividing by the slope, right? So just keep that in mind, because for the next example that I'll do when I generalize it, indeed for absolute values that we have, it will be epsilon always divided by kind of the slope, right, that we have. Because remember, the absolute value is a linear function, except it has the kink, right, which makes it always being positive, right, unless you start to translate it. So let's open up decimals and see what happens here. All right, so there you have it. Okay, so this is, okay, you have, notice you have your epsilon, okay, within here, so there's your delta. So delta is epsilon over 3, and notice it perfectly fits in here. So we have that, and we can certainly, start changing, okay, these epsilons. So going back and forth, I've just readjusted the whole thing, made the c is equal to 3. You can make this bigger. Whoops, that really blows it up. Okay, so let's do that. All right, so here you go. Okay, so you can see that for the delta, so when we are within the delta, we are in fact, okay, within an epsilon away from the limit, okay, for our function. So there you have it, and you can of course make it bigger. Okay, you can make it smaller, whatever it is, and it's adjusting it as you go along. Here's the generalized case, right? So as you can take a look at this, all right, so let's write it out, and let's find our delta. So this is what you're going to obtain. That h falls off, so that constant will be gone, so now this m, of course, you can take out, and what you're going to get is you're going to get this whole thing, okay, within the absolute values. And now again, you can use the inequality, okay, when you have these two things. So this is like your a minus your b, so this is going to be less than or equal to or m, and then x minus k, no longer in absolute values, minus a minus k, like this, right? So, and if you do that, notice that this k and this k will be gone, so it's negative k plus k, and you just have x minus a, which is exactly what you wanted, which is going to be x minus a, right? Now making this less than epsilon, dividing both sides by m, deja vu, right? This is like the linear case, exactly. And it should not be surprising to you, because the absolute value acts like a linear case, right? So it just means that it's always positive. At least this value would be always positive. So here you go. So that's what you would have. So you can now say that delta is going to be equal to epsilon over m. And that's what you would have right there. Okay? So I hope that these examples gave you a sense on how to do and how to find a delta for a given epsilon when you are dealing with absolute values. So now you have quite a lot of tools, linear, quadratic, cubic cases, okay, so pretty much all the polynomials you can expand on, and now the absolute values as well. So you can't get tricked up about that. And then I'll probably do another one on square roots, okay, so on roots, just so that okay, how can I handle those situations? And then you'll have your toolkit for your epsilon deltas that hopefully will help a lot of people. All right. Thanks for watching. We'll see you in a future video. Bye, everybody.